Hi, pre-calc students. This is going to be Unit 5, Day 5. Today we're talking about more with rationals. And specifically, we're going to talk about this concept of what a slant asymptote is. If you look back on the very first day of notes in your packet, we referenced that there is such thing as a slant asymptote. We know what vertical asymptotes are. We know what horizontal asymptotes are. But there are cases where we would not necessarily have a horizontal asymptote, and instead, we'd have what's called a slant asymptote. So we're going to explore when that is today. And once we're done with that, we'll go ahead and actually practice sketching some slant asymptotes. So I'll tell you that these exist when the function is top heavy. So up until this point, when the function's been top heavy, we've really just determined that there is no horizontal asymptote, which is true. But we haven't really sketched anything like that yet. So top heavy, you kind of stop and say, okay, it's top heavy, no HA. But now what we know is that it's a slant asymptote. And by the way, when I say top heavy, although this is not a huge deal for us in this course, it can only be top heavy by 1 degree of separation, meaning that it's like x squared over x to the first, or x cubed over x squared. If there was more than 1 degree of separation, then it actually is not a slant asymptote anymore. Okay. But what we have to know is that there is no horizontal asymptote when it's top heavy. It winds up being a slant asymptote. So you know what? We're ready to jump right into an example where we make a complete sketch. Notice how I'm using graph paper today. That might help you if you have some at home to take some notes on. So you got f of x equals x squared plus 1 over x minus 2. So we look at this example and we say, all right, let's make a complete sketch of that graph. We'd start by looking at vertical asymptotes, and the vertical asymptote is at x equals 2. And then I would move on and talk about horizontal and or slant asymptotes. But for horizontal, there is none. And the reason why is that because this is top heavy, it's heavier on the top by 1 degree. So what that tells us is that we actually do have a slant asymptote. How do we find a slant asymptote? You're going to perform some division, which luckily we know how to do. We're going to divide x minus 2 into x squared plus 1. And if you're nervous saying like, oh man, polynomial division, no, you can still use synthetic division. You don't have to go back to polynomial division, because if you're dividing by x minus 2 as a factor, what that means is that you're testing 2 as a root. So make sure when you copy the coefficients, here's the one thing that is easy to forget, that since we're missing an x term on top, we have to put a 0 as a placeholder. So bring down the 1. 1 times 2 is 2. Add it to the 0 above to get 2. 2 times 2 is 4, plus the 1 is 5. And at the end, that's my remainder. So how do I use the remaining information to come up with the equation for the slant asymptote? Well, first thing I'll tell you is that you ignore the remainder altogether. And then since we divided a linear into a quadratic, this is now a linear equation. It's the equation y equals 1x plus 2. So your slant asymptote that the graph will approach is the line y equals x plus 2. And we'll see what that looks like graphically in just a moment. But the last two things that we'll identify, and maybe I'll actually come up over here and talk about them. For the x-intercepts, we would set the top equal to 0. And when I subtract 1 to the other side and then think about taking the square root, you know, we're not going to have any real x-intercepts if we get plus or minus I as our solutions. So there's no real x-intercepts, therefore I'll just stop here and say there are none. And for the y-intercept, is there one of those if I plug in 0 for the x's? And it turns out that there is at 1 over negative 2, so 0 comma negative a half. Okay, so when we go to make our sketch here, here's kind of the key difference. When we do our asymptotes, we're going to have to make sure that we sketch a slant line at y equals x plus 2 and call that our slant asymptote. So let's start with the easy one. The vertical asymptote at x equals 2 is right here. The slant asymptote, how am I going to plot that? Well, start at 2 on the y-axis. That's the y-intercept of this line. Use the slope of 1 over 1 to find some other points. And just make sure that you don't draw a solid line through there. You just make it a dotted because it is an asymptote after all. Okay, so there's my vertical. There's my slant asymptote. We also had a y-intercept at -0.5, so that's going to be somewhere over here. And then from there, we got to do some partitioning. And it turns out there's only one thing to partition around here. The only thing you have to partition around is the vertical asymptote at 2. Because remember, you're partitioning around special things on the x-axis. So x-axis would be vertical asymptotes and x-intercepts, which we have none of. So if I test something to the left of 2, like 0, oh, well, we already know what's happening at 0. When we test 0, we get a negative because we already determined that earlier. If I test 3, 3 squared plus 1 is a positive. 3 minus 2 on the bottom is a positive, so positive over positive is positive. So what does that tell me about the graph? It tells me whether it's below the x-axis or above the x-axis in those regions. So when I'm to the left of my vertical asymptote, I have to be entirely below the x-axis. The y values are all negative there, and that makes sense according to where the y-intercept is. Okay. So what we're going to see in this section down here is you're going to see a curve that certainly as I go through the y-int wants to approach this vertical asymptote here. But as I work my way to the left of the graph, it's going to curve around and really want to jut out towards the slant asymptote there. So it's kind of a weirdly shaped curve here, guys. But that's what that part of the graph will look like, okay? And then similarly, if I go to the right side of 2 and I think about that the graph is positive, what I don't want you to do is think about that the graph wants to connect and approach the x-axis. There's no horizontal asymptote here. So the graph wants to hang out with its asymptotes, which are the vertical one here, the slant one here. So I'll see if I can squeeze this graph in here. But you're going to get kind of that similar style matching curve up here. We kind of ran out of space a little bit. But as I approach a vertical, it's going to go up to infinity. As I go to the right forever, what does this graph want to do? It wants to hang out with its linear slant asymptote friend, y equals x plus 2. So that's the general pattern that the graph takes on. And in the beginning of this process, if you're like, gosh, I'm really not sure if that's really what it looks like. I mean, these are going to start looking pretty funky here. I'm going to just really quickly in y equals type in x squared plus 1 in the numerator and x minus 2 in the denominator. So here's what I got here. I'm going to zoom 6 and see if I see these kind of weird looking, they're not really parabolas, are they? There are these weird looking curves. Oh yeah, there's my y-intercept at -1, and then you get that matching curve, you know, right up here. If you want to extend the window up a little bit, you can do that to see the full graph. But yeah, I mean, that's what we got going on here. We got this curve that wants to approach the line y equals x plus 2. In fact, if you were to go to y2 and type in x plus 2, I bet we can see that the graph is really doing a good job approaching that. Look how cool that looks, right? So on the calculator, it does a nice job of showing, yeah, as we go to infinity and negative infinity, the end behavior is we're not approaching a horizontal line, we're approaching that diagonal line, y equals x plus 2. Okay, so hopefully you can use the calculator to your advantage if needed when double checking things like that. Let's try another sketch where I give you x squared minus xy minus x minus 2 equals 0. Okay, so we're going to make a sketch of that rational function. Well, it's not looking too rational to me. It's not even a fraction. Fractions are rationals, aren't they? Well, I bet if I solve for y, it will turn into 1. Let's see. So in order to get this solved for y, the easiest thing might be to do to like add xy over to the other side. So x squared minus x minus 2 equals this positive xy now. Dividing the x to the other side, I'm just going to keep y over here. You're going to get this equation right here. X squared minus x minus 2 all over x. That's looking nicer to me now. Okay. And in fact, one important thing to do, I think, when you have these situations is, you know, factor the top and bottom to see if there's any holes in the graph or anything like that. So when I factor the numerator, it's going to be x minus 2 times x plus 1 all over x. So let's start finding our key information here. We have a vertical asymptote for sure at x equals 0. Horizontal asymptote, there is none because this is top heavy, right? We have 1 degree higher on the top. So when I do my slant asymptote work, I'm going to use 0 as my root to test. Actually, it's the vertical asymptote always, guys, right? If you come back up here, 2 is the vertical asymptote because that's the factor that we're dividing by. All right, and the coefficients are 1, -1, and -2. So bring down the 1. 1 times 0 is 0. So plus -1 is -1. And then this becomes 0 again. So the remainder is -2, which we don't really care about. The slant asymptote is at y equals x minus 1. All right, from there, we got to find some x-intercepts. I'm going to put plural there because I know we have 2. Since I already have the top in factored form, I know that we have an x-int at 2, 0, and also at -1, 0. And last thing for now before we get to the graph is there a y-intercept when I plug in 0 for all those x's? And it turns out the answer is no, because we can't divide by 0. So it makes sense because there's a vertical asymptote right on top of the y-axis, so there is no y-intercept. All right, we did that kind of quickly there, but at the end of the day, we can do our partitioning to figure out what this graph's going to look like. Okay, so we had x-intercepts at +2 and -1. We have a vertical asymptote right on top of the y-axis at x equals 0. So we'll include that. And then x minus 1, that's the slant asymptote. So we want to make sure we start at -1 on the y-axis and then use a slope of +1 to get a line that looks something like that. Okay. So we've got all our asymptotes in there now. What on earth does this graph look like? Well, we have a couple partition points. We have to partition around x-intercepts, vertical asymptotes, and the other x-intercept over here. So with all that included, we have a couple of regions that we're going to have to test in to see what the graph looks like. So if I test something to the left of -1, like -2, -2 minus 2 is negative. -2 plus 1 is negative. Plugging in -2 to the denominator would also be negative. Negative times negative is positive, over negative is negative altogether. Now I'm doing that pretty fast, guys, but make sure you're understanding it, how we're getting positives and negatives in these regions. We've done a lot of partitioning this year, so we got to be pretty solid with it. Test -0.5. -0.5 minus 2, still negative. -0.5 plus 1 is positive, though. -0.5 in the denominator is negative. The top is negative divided by a negative is positive. And just to kind of shorten this up a little bit, I'll tell you that the signs do alternate for this one. So if you don't believe me, double check it. But this would be negative in the next region. This would turn to positive. Do the signs always alternate? No, they do not. Okay, but in this scenario, they do. So what am I going to do? I'm going to go from, to the left of that root, I'm going to go from negative to positive. Same thing happens over here on the other side of the vertical asymptote. I'm going to go from negative. Once I hit the root, then I turn to positive. So you saw me trace those paths here, but I hope that the partitioning makes sense. That negative means you're below the x-axis and the graph wants to get really close to the slant asymptote. Once I hit the root, then I'm going to head up towards the vertical there. Okay, so this whole tiny little section of the graph is positive. Then we go from negative from 0 to 2. Once I hit the root to 2, we're going to be above the x-axis, but remember the graph wants to head off towards its slant asymptote friend, y equals x minus 1. So it takes a little while to get used to this because we've seen some very similar-ish looking graphs over the past few days. Slant asymptotes are a whole new game. They start looking really different, okay? We're going to do one more in today's notes, and then, of course, a lot more practice to come. The last one that we'll do is, let's take a look at number 3. We'll do x squared y minus x cubed minus 1 equals 0. So similarly set up to the last one where y is not alone, you're going to start seeing this a little bit more often as you get through some practice. So for this one, I'm going to add x cubed and add 1 to the other side. So now it's x cubed plus 1 over here. And finally, dividing both sides by x squared would make it such that this is our rational that we're going to sketch. Okay. So we talk about vertical asymptotes. We get a vertical asymptote in this one at x equals 0. If you said x squared equal to 0, square root, you're only getting the vertical asymptote at x equals 0 there. There is no HA again because it's top heavy. So to find the slant asymptote, we've approached it from synthetic division, but it looks a little weird when you're dividing by x squared, doesn't it? And it turns out that I could have done this in the last example as well. When you're dividing by a monomial, you can just divide each of the terms in the numerator into, by the denominator there. So rather than doing synthetic division, as long as it's a monomial, not a binomial term, you can, to get the slant asymptote, just divide out x cubed over x squared plus 1 over x squared. Right? That makes sense. I can split that up because if they have the same denominator, we can add them together again to get back here. But x cubed over x squared is just x. And what is that 1 over x squared? That's the remainder that you get from dividing. So y equals x. This line right here is the slant asymptote. We ignore the remainder when we're dealing with division for slant asymptotes. The reason why you can ignore the remainder, guys, is we're thinking about as x gets really, really big, what's happening to the graph? Well, as x gets big, this whole thing's going to 0 if x is a large number. This is why the remainder kind of is insignificant as x goes to infinity. All right, so then we have the slant asymptotes. Do we have any x-intercepts? If I set the top to 0, x cubed plus 1 equals 0. Yeah, if you subtract 1 to the other side and then take the cube root, the cube root of -1 is -1. So you have a real x-intercept at -1, 0. The reason I phrase that way is we know x cubed has 3 solutions, but the other 2, I'll tell you, are imaginary. And for the y-intercept, if you plug in 0 for all the x's, well, with x squared on the bottom, dividing by 0 is an issue. So there is no y-intercept. So when I come over to my sketch to see what this graph looks like, we know that we have a vertical asymptote at x equals 0. We have a slant asymptote at y equals x. And an x-intercept over here at -1. So we have 2 partition points, one at -1, one at 0. So you're going to want to make sure that you're testing in each of these regions, right? If you test -2, -2 cubed is -8, plus 1's negative. -2 squared. Bottom's always positive, isn't it? When you square a number. So the first region's negative. We test -0.5. I'll tell you that you're going to get positive. And then finally, if you test something like x equals 1, you'll also get positive. So again, the signs don't always alternate. Around x equals 0, you go from positive to positive. So what is that going to look like? Well, to the left of the root, we're below the x-axis. That makes sense. We're going to approach the slant. Once I go through the root, I'm going to approach the vertical asymptote and be positive. All right, no more x-intercepts on this side. So what does the last part of the graph look like? Remember, the graph has no reason to hang out with the x-axis. There's no horizontal here. So it wants to hang out with the vertical and the slant asymptote. And that's, again, it's a really weird looking graph in the end, but when you put all the pieces together, that's what this sketch should look like. So that's it for me for slant asymptotes for today. Much more to come with this. We'll do a lot more practice because I know these can start looking pretty weird. But when in doubt, check on your calculator for now. Have a great rest of your day.